Welcome everybody today to our session of iTrain with the European Arc Network. And today I'm very happy to have here Miroslav Barta from the Czech Arc node. He's one of our well-known experts on solar ALMA data. And today he will explain us what it is about observing the sun with ALMA. So please, Miro. Thanks.
Okay, Carmen, many thanks for inviting me to this course, to this webinar, and I will be happy to somehow in 1 hour you can present just the basics, but it will be some attempt to demystify the solar data observed with ALMA. So it will be just introduction to basic data analysis and processing. So let me first start. I have a few introductory slides, like 15. I don't want to spend too much time with that, and rather we will go directly to the hands-on session, and I will describe all the features that I will speak now at these slides directly on the software and the scripts. So we will process this iconic sunspot, which is almost 150 pointings, big, very large mosaic in band 6. These are commissioning and science verification data that were taken in December 2015. And the primary source of the data, you can see the link here. And so that there you can download everything. And for the purpose of this training, I reprocessed the data with, say, new CASA version. I wasn't able to really make it working in CASA 6.4. But eventually it works with CASA 0.56 calibration, and imaging works even with CASA 6.4. And here, this link you received with the invitation email, and you can see the data completely unpacked because it's like in the middle of processing stage. So you see all the diagnostic plots and everything. And I will open this data and show you the specifics of solar observations. So let me first introduce what are the specifics of solar observing mode. So first, why to observe the sun with ALMA? Of course, there is a lot of key science questions that solar physicists would like to answer, and ALMA is absolutely great tool to help. It's not an exception, it's in entire astrophysics. So all you know that ALMA is absolutely great instrument, and all we wish to have it. Moreover, during the daytime, sometimes the humidity can be higher, and we have a bigger absorption. Still, we are able to observe the sun, so it is some, say, meaningful use of the daytime. So this is the reason why to observe sun, and why it is not so easy. Why we cannot do the standard procedure, as you know. I suppose that you already participated in the training about basic interferometry, about the basic data processing. There are several peculiarities of the sun. First, the sun is hot. We have a big heat flux. This is a priori solved. ALMA already counted with that the sun will be observed. So the surface of the mirror is not absolutely polished. It's a little bit rough, so that it is like very, very flat for the millimeter and submillimeter wavelengths, but for the infrared and optical radiation, it is not already polished, and the radiation is scattered, which prevents the heat flux. What is worse, that sun is even far brighter in the millimeter and submillimeter wavelengths. So this is a problem with the dynamic range, because we need to observe, for example, a flux and phase calibrator, which are relatively very faint in comparison with the sun. Yes, so this makes troubles. We need specific calibration procedure. We have to somehow independently observe what are the antenna temperatures, because for most of the sources, antenna temperature is negligible with respect to system temperature. And basically what we are doing in interferometry is collecting this very tiny signal above the lot of noise. With the sun, it is vice versa. We have variability on the short time scales. The sun is changing. Of course, galaxies are also changing, but not. We are not able to resolve the spatial scales where we could really see the dynamics. But with the sun, yes, because the sun is much closer. So we need time domain imaging. Instead of having a snapshot, we would like to have a movie. And because of phase variations in the atmosphere would be like shaking, we need to do some self-calibration methods. What is even worse, we need instantaneous UV coverage, because with the galaxy you can use Earth rotation for aperture synthesis, and UV space is covered by projection of the baselines. We cannot use this because, as I told, the sun is changing. So we need really instantaneous, pretty dense UV coverage. The sun is moving, and not only then the sun is moving in right ascension declination coordinate system, but the sun is rotating, and the objects at it are moving even with respect to the solar disk center. So the situation is similar like if you observe asteroid or comet. We need some specific ephemeris for that. Only the dynamics is different. It is not celestial dynamics, but it's more or less plasma dynamics at the sun. But to some extent, we can do prognosis, forecast, where this sunspot, for example, will be next 2 days, and calculate ephemeris for that. And solar physicists, it's connected with that. Solar physicists are used to use absolutely different coordinate systems that are centered to the solar disk center. And many solar instruments are producing images in this so-called helioprojective Cartesian coordinate system. So if you would like to co-align with other instrument, you need to do the transformation. And one of the very important things, we have always the emission that is filling interferometric field of view entirely. So in order to have some absolute brightness temperature or flux density, we always need to do TP and interferometric data combination. Otherwise, you stay just with the differences. And now it looks very like generic or generous, but you will see in further how this general ideas, how they project into concrete troubles. So this extreme solar emission, the thermal flux, as I told, it is easy. The reflectors are a little bit with rough surface, so you can see that we are not baking the detectors. the thermal and optical flux is really scattered, and we are able to point to the sun without troubles. The bigger trouble is with this solar emission, that it has also very big millimeter and submillimeter flux. So for that, we need to adopt a procedure that is called mixer detuning. Here you can see the standard, more or less, it's a so-called list ops 3 task that produces you development time expansion of the different scans with different purpose or targets which you do. And if we apply this scheme for the sun, we are using two setups. One is this like standard ALMA settings, which means that we are observe the entire signal that is coming to us, which is for bandpass and phase calibrators and for the atmosphere, but for the sun and for the flux calibrator, which for that reason we have to always find a really strong flux calibrator. We have to we have to attenuate the solar signal because it is too way strong, and the detectors would be saturated, right? So even before the data are digitized, we have to attenuate electronically the signal. This procedure is called SIS mixer detuning. And the point is that you see we are observing flux calibrator and the sun with this attenuated setup. So you can imagine that it's equivalent like putting some filter or attenuator into the optical path, while the phase calibrator is observed not attenuated. We did during the testing a lot of tests whether this attenuation can somehow influence also the phase of the phase calibrator, and fortunately it doesn't. So we can do this trick that we observe the sun, this attenuation, and the phase calibrator without attenuation, and still we have a good phase the calibration like on this long time scales. So this is observing setup which assures that we are not saturated when observing the sun. This has another, this extreme millimeter and submillimeter solar flux has another issue, which is this T antenna, the T ant, that the T ant is absolutely not negligible to with respect to T-cis. I have an impression, correct me if I'm wrong, that it is very much connected with this issue of renormalization that appeared. And I also borrowed this formula from Luke and Andy's presentation about renormalization. How standard and also ALMA calibration procedure works on. So we have these correlations and auto correlations, and via this you renormalize. In the case of the sun and antenna, transform to antennas, this correlation coefficients rho mini transform to this. This is from Masumi's and all paper. That you see that this autocorrelations that they contain T ant plus T cis, and usually you have this T ant negligible. Only for a very strong line emission, which appears with this renormalization issue, you can have T ant non-negligible. But with the sun, we have the T ant always much bigger than the T cis. So you cannot neglect it, and we have to have some independent estimation of this T ants. And how it is done? Basically, we are using SQLD detectors that are in ALMA present as well. If you look into list ops, you see that you have a long list of SPVs, and actually only 4 SPVs are then used for science, because these are these channelized spectral windows. Then you have here these SPVs with channel averages and water vapor radiometer spectral window, and there are also SPVs for these square law detectors. And from them, we can basically calculate this antenna temperature. So it is always that we are like, we have observing nothing, like dark current. Then we observe sky, which is sky its atmosphere outside of the sun. P of is atmosphere outside of the sun, but with this mixer detuning, we have 2 setups. You have to remember this mixer detuning switched on and off. So one is with on and one is off with off. And from that formula, we can estimate from this SQLDs, we can estimate independently T ant and put it here and make the normalization. So this is important step that is not in standard calibration, and we will see it later in the script. Then, as now I'm going one issue by one, which we have this is specific for the solar system. As I told, we need instantaneous dense UV coverage. So we cannot even give up from this combined 7 meter, 12 meter antenna baselines, because it's also significant number of baselines, and therefore significant number of UV points in your UV coverage. So on costs of that, we are using heterogeneous arrays, which has other issues. We are doing it. So in solar ALMA observations, we are using this kitchen sink array, which means that 7 meter ACA and 12 meter baseline correlator, everything is connected into one correlator. So we are calculating even 12 meter, 7 meter correlations that are present in the data. So this is how we cope with this trouble. This ephemeris, of course, you have to have some prediction of where, for example, this bright feature at the sun will be at the day after tomorrow, because it is usually as a contact support scientist, I'm in touch with astronomer on duty, and in the scheduling I know that in 2 days the observation takes part, And so we have to communicate with the PI, and we have to submit together ephemeris and check whether it works. So there is by Ivica Skokic, he implemented the so-called ephemeris tool. So you select a region at the sun and press a button, and it automatically calculates right ascension declination as it will evolve with the time for next 2 days with 15-minute cadence. And this you submit to ALMA observing software, and it is attached to your measurement set. And later we have to somehow revoke it from the measurement set in order to set your data to the proper reference frame. A little bit connected with that is this problem of transformation from right ascension declination to this projective coordinates. So we have another script. It's already belonging to this, say, advanced post-processing of the data. Fortunately, it is not so difficult with Python. We have SunPy and AstroPy, and it provides this transformation routines. So in Python, you on a couple of lines, like 50 lines of the code, you can make a script that transforms the right ascension declination data to this standard solar coordinates, and you can do then alignment with the other instruments. Another topic which is important is the total power maps, because as I told, if you would like to have really brightness temperatures and not just differences, you need to combine interferometric and total power data. And because the sun is varying very rapidly, there was a task how to make a total power map of the sun very quickly. And the standard rastering that you are going with the antenna line by line, it takes ages. So there was another idea how to make it, because it's mechanics of the antennas. It is much easier for them if they move in the pattern that is indicated here. We call it double circle pattern. So it makes like circles, and the guiding center of this circle is like an epicycle. It's going on the bigger round, bigger circle. I don't know whether you will see how the movie. Probably not. I will have to share it separately, but no problem. I have a movie how antenna is really doing it in a real time. Nowadays, so far we are doing this full disk solar map. So it means that we have a mapping of the entire sun. Of course, interferometric image is much smaller. And I have good news for you. Yesterday there was go no go observing mode development meeting, and we got green light for the new feature of the solar observing mode, that we will be able to do regional total power mapping, which will have a much higher time cadence and will be more practically better for combination with the interferometric data. Anyway, we still need the entire solar disk. Why? Because we are using the quiet solar atmosphere. We always select some region near the solar center as a calibrator. Yes, because you know, for example, that we are using solar system objects like Neptune or some moons like Titan as a calibrators. How we do it? Because we have pretty good models of their brightness, and the same is the sun. We have pretty good models of the quiet sun, and there is no this activity, no this brightness feature. We know pretty well what should be the brightness temperature. So we have to always make a total power image of the entire sun, and select some area as a reference point, and then for that reference point we can attribute the absolute brightness temperature because of our good model. And then we have some if later next cycle 9, we have this regional local total power map, and again we have some reference point that is displayed both in the regional map and the full disk map, and this way we can tie together the brightness temperature and the regional map to the full disk map. Okay, so what are the specific features which we will see very soon in the data? So in calibration, first, theses are much higher than you are used to. You are used to like 150 kelvins or whatever. We have much usually like 2000 kelvins and more. Why it is? It is because we are using this mixer detuning mode. I will explain in practice later when we will see the data and the diagnostic plots. As I told already, we have the necessity to calculate independently T-ant from the SQLD. There is a library of routines which is called sun reduction utils, and they are present in the data and software that I submitted to you. And there is a routine which is called sol-amp-cal2, and this makes these calculations. And not only that we have to calculate this T-ants, but we also have to check this T-ant plots, whether they are correct. Usually we flag some antenna based not so much on thesis, but on T-ant plots, because we are always very cautious in flagging entire antennas. As I told, we need this instantaneous UV coverage. So always, I'm almost crying when I have to flag entire antenna, because it's not only lost in sensitivity. This is trouble for, say, galactic and extragalactic and other faint sources, but for us it is a loss of UV coverage, and it is critical. Flux scale. Always you flux scale the secondary calibrator, and then you compare with the database of calibrators to double check whether your calibration procedure is correct. Here it is not always working. If the secondary calibrator has been observed with this not detuned mode and the primary calibrator in detuned, then you cannot expect that the values will be correct. So we have to take this into account. Always we have to attach ephemeris to the calibrated dataset. So we are using another step at the very end of the calibration script, which uses fixed planets, and it attributes the correct reference frame to the data. So this is with calibration. This imaging, interferometric brightness maps merely the difference to the average background. So people are always scared when they see solar images, and there are values like plus 50, minus 100. What is it? What is the temperature of minus 100? How is it possible? Because we are observing just the differences to the average. Cleaning is very specific. We are cleaning class ages as well, because we are using a lot of cleaning cycles, usually multi-clean, because we have diffuse emission, which has usually not so many very significant structures. So it is difficult. We have to be very cautious when cleaning. Usually we have to limit a number of minor cycles before doing a major cycle. Otherwise, you can run into instability, and so the cleaning doesn't converge. So this is something you have to observe. Now the issue of the heterogeneous array, because the PB core, we have to be again careful with doing that, because we have this 7 meter, 12 meter combination baselines. So the calibration and imaging, this is like some basic procedure which we are doing for QA2 to deliver the standard ALMA data products. They are then ingested into archive and submitted to the PI. And of course, there is a lot of other post-processing that you need in order to get really science-ready data, because this basic QA2 procedure, its main purpose is to prove that the data are ready that the science analysis can be done with them, that the observation was correct. So this includes interferometric and total power data combination. Not always you really need this. If you are looking for example, some local heating phenomena, like that some shock wave evolves in the solar atmosphere, you may be interested just on the temperature increase with respect to the background. So interferometric image is fine if you don't need really absolute total brightness temperature. But most of the people would like to have it. So this interferometric plus TP data combination is necessary. I will only touch it briefly, show you the script, how to make it using feathering. Then there is this time domain decomposition, which practically is working only for a single field and small mosaics. Again, if we have time, I will show you the script, how to do it, how to get the image just for selected times in a loop. This is connected with self-calibration because you have to somehow stabilize the image if you would like to make a movie. Otherwise, the movie is shaking and changing the brightness, and all these apparent motions and changing of the brightness are only partly on account of the solar dynamics. Most of that is because of the phase errors which you have from one to another frame in the movie. So you have to do self-calibration. This I'm already not going to touch. And to coordinate the transform, I have shown you that it is possible to do this simple Python script using SunPy and AstroPy routines to make transformed from right ascension declination to solar coordinates, which allows you to do co-alignment with the other solar instruments. So I will stop here with, and now I will share the calibration script, and we can go step by step. You see the window with the script.
Yes.
Okay.
We have a question that maybe you can also respond because it's related to the calibration. The attenuation that you explained at the beginning, because the sun is so strong. There is a question. Does this electronic detuning for attenuation have some impact on the bandpass shape?
No. This we checked that for the it doesn't introduce like error concerning the spectrum, and it doesn't introduce this is just very small error for phases. So basically the attenuation really looks like if you put some gray filter in front of the antenna, fortunately. So there is still some troubles that the attenuation doesn't work. We a little bit increase our dynamic range, but still not sufficiently, for example, for observing of the solar flares. If you have a major solar flare that occupies a significant portion of the field of view of primary beam of one antenna, then we are lost anyway, because the attenuation helps somewhat, but not many orders of magnitude. So for this purpose, probably there will be these real filters. They started to be developed at the beginning. It was the original idea to use this. Later, it was found that these filters have some issues with maybe even band pass. This I don't realize, but definitely with the phases, that they introduce also phase delay, and the phase delay was somehow very badly reproducible. That one day you put the filters there and measure what is the phase delay introduced by the filter, and a few days after the delay was different. So it introduced the necessity to make this calibration of these filter devices very frequently, which is very impractical. Yes. So that's why we so far got rid of that and using this electronical attenuation, but still, because we would like to observe also major solar flares, the flare mode is something on the wish list of the solar community, and perhaps in the future cycles it will be introduced as well.
Okay, thanks. No more questions.
Okay, so now I hope that that the window with the script is shared.
Yes.
Yes. Okay. So basically, these steps which we are doing with the sun, they are very similar to what we are doing in a standard calibration. So you see import and this syscal table. It's already it is included there for the case of all the data, but nowadays this trouble is not here. And what is specific here is this thesis and T-ant calibration. So for this solar script, it's a little bit differs from the scripts that you may know. I try to make it a little bit automated. So some parts that now come into so-called solar script generator are now inside the script. We try to diminish the possibility that the QA2 analysts make some omission, some error that implies from that you are copying a template from one script from one data set to another, and then you forgot to change, to edit something. So it's better to make it more automated. So that now they are at the beginning in the preamble of the script. You needn't to study it into depth. It just makes these things which standardly solar script generator does. So it from the intent, it realizes what is the phase calibrator, what is bandpass calibrator, which field is the flux calibrator, whether we are mosaic or single field observation, and so on. So there are many these guesses, but after you did this preamble, you go through the steps. So standard import of the data, this fix of the bug that is not appearing anymore. A priori flagging is the same as usually, that you are basically getting rid of the things that you don't need anymore. And here, yes, we are doing also antenna position corrections, but this is more or less the same as in standard data. What I would like to show now is the typical antenna and antenna and system temperatures. So this is what I told. You might be scurried with the system temperature. Yes, you are used to values that are like 150 or whatever. Here we have much higher. Why it is so? It is basically, if you recall, how the system temperatures come there. So, for example, for the system temperature, which is at ALMA, mostly given by the atmospheric temperature. So imagine that you have transparency of the atmosphere is like 50%. So your system temperature is like you see 50% of the signal of your target plus 50% of the kinetic temperature of the atmosphere, if the transparency is 50%. And now, when we are introducing this attenuation, we have like additional atmosphere, or so to say, we have additional filter or additional attenuation factor there, and this is the reason, because ALMA software is not it doesn't count with that you put some additional attenuation there. So this is the reason why we have so large thesis. Yes, so you see that it is like 6 times or more higher than what you would expect normally. Anyway, still you can see, for example, here these are the atmospheric lines which are present there, like in standard data, and we flag the antenna if it is if there is some really pretty high system temperature, or if there is a really big difference between XX and YY component. So I'm trying to find some really bad antenna. So it looks like this is pretty fine. And what you have to also check is this T-ant temperature. So first, let me show you in the script. We are calling the procedure that is called SolAmpCal2. If you are interested in it, share. So this is what you can see. This is the collection of the library of ALMA, solar ALMA routines, and I can find here. So let's so AMPCAL2. So AMPCAL2. So AMPCAL2, yes. So now I got it. And if you look, if you are really interested in depth, here you can see how basically it is done in line with the formula that showed you before, that we are finding this p zeros, p sky, and p off for attenuated and not attenuated signal from the spectral windows of SQLD detectors, and calculating T ant for every antenna. This procedure, unfortunately, is the longest one that takes really lot of time for calibration. So this is the most consuming CPU time procedure. It takes sometimes more than 1 day for a large data set. So okay, I will share back the script. So you can see where is it. So it's in the step 5 or 6. So again, yes, I kept this standard flagging, and in yes, this is calculation of antenna position corrections, and now we are doing apply cal for of thesis and antpos to calibrators, but for the sun you have to do something different, and for the sun we are using this sol al camp2, which is the routine from the library, which I showed you, and it calculates this T ant temperatures and makes the normalization of correlations, including T ant. In this sol AMPCAL2, you can select whether you would like to neglect or non-neglect the weights. Quite recently we found that if you have an observation that contains a limb, so the edge of the sun, and it is a mosaic, that it can happen that not only that you have to calculate this T cis and T ant, but because this T cis and T ant are added together for calculating the weights, and the higher is the T cis, the lower is the weight of the field. We had an artifact that the fields of the mosaic that has been on disk had much lower weights than the fields of the mosaic off disk. So they sometimes disappeared. So for such a case, it is desirable to switch the weighting off, and don't use T ant plus T cis weights for weighting, because these off fields, of course, they have much lower T ant than the fields that are at the disk. Then the other steps are again pretty much the same, like in standard calibration. Here we flex some antennas based on T cis and T ant. So for example, here we flag T ant for antenna DA52. So let me once more to stop sharing this and show you how the T ant graphs plots look like. Okay, so these are the antenna temperature plots, and you see that they are fine, that we have against some QA2 criteria what should be the antenna temperature for different frequencies, and it looks like that there was some like atmospheric scan or some off scan that was outside of the sunspot. So the antenna temperature dropped, but otherwise the antenna temperature here is fine. It's what you expect, what should be antenna temperature of the sunspot. And so let's find the antenna that is wrong. Aha, you see, this is DA52, and you see that it has completely wrong values for many scans. So this is the antenna that you have to flag from your data set. Probably it had already bad thesis. Usually it is connected. When you have bad thesis, then the ant also is wrong. But the other antennas are okay. So we have to check these plots. Let's go back to the calibration script. So we are back. Here the rest of the script is more or less the same as the standard scripts for standard data, standard non-solar data. But what we have to do as the last step is this calculation of the direction where the antenna is pointing. In earlier data sets, we used so-called antenna sensors, but it wasn't pretty much accurate. So since cycle 5 or 6, we are using different tool, which is based on metadata tool. So you have this MSMD, and for that you can find some reference time for the very first science data scan, and to this reference time because as I told, the sun is moving. So for that reference time, we put all the data, we stack all the images of the sun to that coordinates rectangulation declination where the frame was at that reference time. And how we do it, basically this MSMD data, we are able to access our ephemeris file, which we submitted to the astronomer on duty before observation. So the ephemeris file is still present in the measurement set, and to each solar field, when it is a mosaic, we can attribute right ascension and declination, extract the central positions for the reference field 0 from the ephemeris, and then for the other fields we have offsets with respect to this reference field 0. So we are for each of this offset we are also able to calculate the right ascension declination, and then using fixed planets we put these directions to this sun phase there for each of the field. Yes, we have a loop for every field of the mosaic, and for each of the field we extract the offset and add it to the ephemeris of the reference field, and using fixed planet we can attribute right ascension declination to that field. And that's all. So this way we are doing calibration of the data. It is also nowadays in modern CASA to use track field option in T-clean, but my experience with that are quite sad. It didn't work, or at least it didn't work for all the data. While this is this method is working perfectly, and the alignment after it is quite good, quite exact. So we are using this way that we put right ascension declination to every field of the mosaic in each step already in the calibration. Okay, so calibration is finished with this. So I would repeat in order to demystify these solar observations, the key points. We have to calculate independently T-ants and check the T-ant temperatures, because and theses are much higher because we have this mixer detuning system. Flux scale may not work for the secondary calibrator, and we have to use this SOL-AMPCAL tool for normalization of the data in order to have correct normalization, which takes into account the thesis plus t ant in the denominator. Before I start with looking into imaging script, I will show you the reference image, reference picture of the just interferometric data. And now you can see the values which are under the cursor. And you can see that, for example, in the center of the sunspot, you have minus 113 now. And here you have plus 100. So how it is possible? Normally you think if you have standard interferometric image that you have absolute brightness temperature or Jansky per beam or whatever, some absolutely calibrated value. But you have to take into account what we are actually observing with the interferometry. We are observing interferometric components and Fourier components. And what is the Fourier component of the average signal? It is a Fourier component with U0, V0, but this is never present in interferometry data. There is always a hole. So we don't have the background. And these data which are here, they are just differences to the background. So even if you have non-solar data, you have differences to the average, to the background. But because in the, say, galactic observation, the image looks like that you have darkness everywhere and somewhere in the middle is a small object. 99% of your image is zero, is no emission. So the average is a zero. So when you then have interferometric image, you have slightly minus outside of the image, and the values that are inside of your target, they are almost exactly the real absolute values. This is because the weighted average is very close to what you expect, but with the sun not, because you have emission everywhere. Yes, so the average has to be revealed by some other method, and the other method is of course total power data. So this is another like mystery that people see when they look first on the interferometric data. So now let's go into the imaging script. So all the data here, which I put you the link, you have in this form that they are like under processing, so you can see them. And so I put everything into calibrated as usually, and script for imaging. Okay. So again, there is a lot of automatism that try to set automatically what should be the cell size and what should be the image size. There are some typical values that are suitable for fast Fourier transform, and based on that we select the image scale. It is so that's why this script is so lengthy, but you needn't to really worry about that. It is just automatic setup, which helps you to make less mistakes and set up the parameters of T-clean properly. So what we are using here as a deconvolver, we use multi-scale. It can be different to the others. We always limit this cycle and iteration, which is iterations of the minor cycle, because otherwise we have troubles with instability, as I told. Spectral mode is multi-frequency synthesis, because with the sun we are not observing in spectral resolved mode. The grider should be standard for single fields and mosaic for mosaic. It is important to set it correctly for that reason that I told you that we are using this heterogeneous arrays, that we have 7 meter and 12 meter combinations, and somehow the gridding procedure is the procedure that takes care of that and sets proper weights even for this and proper shapes of gridding even for this combined data. I mean that are correlations between 7-meter and 12-meter antennas. Because the processing is pretty lengthy, we cannot use masking. This is another point. You know, if you have emission just somewhere very close to your center, then you can set up the mask and everything then works much smoother way. So we cannot, that the processing is very lengthy, so we are using MPI usually. So it's really worth doing start CASA, this not CASA but MPI CASA, and use if you have some cluster, some parallel device, then it really helps to increase the efficiency, because this major cycle which we are repeating more frequently than in standard data imaging, they are done in parallel with MPI CASA. Anyway, imaging also takes like 1 day if you don't have any starting model. So this is the difference for the imaging. The main, if I should repeat again, the main difference or main what can scare you is that you have just the difference to the background average signal. So which means that you have plus and minus signal equally distributed in your image in when you do this solar imaging. So this was the interferometric data. I'm running out of time, so very quickly I will go through calibration and imaging data for the total power. It is basically easy. Share. I can see it. Share. So I hope now this SD data script is shared. Again, there is some automation which helps, and then again it also the image size is depending whether it is band 3 or band 6, because we have different resolutions. And here basically the imaging is again pretty much standard. What is not standard is here that we are like scaling the image towards the region in the center that we selected at the sun, and in kelvins, because this is what I told you, that as for some purpose we are using Neptune or Titan or solar system bodies as a flux calibrators, because we have pretty good models for them. The same, we are using the quiet sun regions, and there is somewhere implemented what should be quiet sun level. For example, here for band 3 should be 7,300 kelvins. So this is how we tie the values with the solar total power data, this brightness temperature. And for band 6 it's 5,900. So this is these are these model temperatures for quiet sun regions, and here we select some region near the center, and in that center in that region we do statistics, and for this average is attributed this value. Yes, so this is how we put the absolute value to the total power data. Otherwise, the calibration and imaging is done by standard is as the imaging task. Nothing really different to non-solar cases. And because time is really running out, I would just show you what are some more advanced procedures, because with doing this, we are basically finished with this basic data analysis and imaging. These are the products that we deliver to the PIs, interferometric imaging of the solar object, just a single picture integrated over all times, and solar and SD data, SD single dish image, again calibrated data for the entire sun. And if I go calibrated, here it is, advanced imaging. And so just showing you how we perform the combination of the data. First, before doing feathering, we have to select at the total power data the same region as it is for the imaging data. So this is some mathematics that you have to do in advance, and then basically you combine the data using standard feather task, and finally do primary beam correction. And again, you do this recalculation to kelvins. So it is again not very pretty much different to standard data combination. Simply we are using feathering and then rescaling to kelvins. Only what is here and what makes more complication is that we have this total power image encompass entire solar disk, while interferometric image is some defined region. So you have to first crop the big image and select just the region which you have covered by the interferometric data. Since cycle 9, this will be better because we will have this regional total power mapping. So first we will have a higher temporal cadence, and also the overlapping between interferometric and total power data will be more easy. So this is one thing which you should take into account in this advanced imaging. And the last one, which is not worth doing here for this large mosaic, because revisiting the next field, it appears after a very long time. We have 154 pointings. Each pointing takes 7.5 seconds. So it doesn't make a sense to have time domain imaging in that. But single fields or very small mosaic, you can do it. And basically the key point there is that using either a table data query or metadata MSMD tool, you find the times for different subscans, different integrations. And then what you do, you basically make this standard QA2 imaging, set this time averaged image of the sunspot, which I showed you before, as a model, because it speeds up the cleaning pretty much. And then in a loop, you basically send into tclean this extended the extended number of parameters, and you put there a time range. Yes, so now you are not imaging in this loop. Every loop doesn't image entire measurement set, but just a given time range for a given subscan. So this is the way how you can make easily, or not easily, but straightforwardly, basically the series of the images, which you can then combine in some external tool. If you have many, for example, PNG images, you can combine them into a movie and make a solar movie. The problem here is that as I told, there are, in addition to real solar dynamics, there is also this apparent dynamics because of phase errors, and the task to distinguish between these two it is like a hard task and much more advanced topic that I cannot present here. If you are interested, the Solar ALMA team is organizing solar imaging workshops. Oslo University is very active in that, and that there was one workshop last year face to face, and 2 weeks ago we had a similar workshop organized as a webinar, and I guess that in 1.5 years, 2 years there will be another one. So if you are interested in this more advanced troubles of the imaging, then I advise you to attend such a meeting. Okay, my time is over, so thank you for your attention. I'm sorry that it was so chaotic that I had to always switch between different windows.
It's okay. It's
yeah. So I hope that the solar data are now not so big mystery. The key points are that we are using this mixer detuning. We have to calculate T-ant and basically do the renormalization always. What is now issue only for some data, non-solar data, but we are doing always all the time. And there are some differences with the imaging. And also don't be scared that you have different theses, much higher, that you have to observe the T-ants, that they are correct, and if not, then flag the antenna. And also don't be scared that your values in the interferometric image are equally plus and minus, because this is normal if you realize what interferometry is, that it is Fourier imaging and you don't have the background level because lacking zero component. Okay.
Thanks, Miro. It was very clear. I think, yes, something that perhaps is important to stress after all your detailed explanations about calibration and flagging and all that is that in principle, when we explore the archive and we get the data, this has been done already by someone as expert data reducer. It's always good to check, as you said, that it's important that we get used to check the plots and make sure that the antennas are fine. But it's not that the final users are supposed to be worried about. It's just in principle that this is the work that is being done.
Exactly. Yeah. This is basically it is. Sometimes people in solar community are unhappy that ALMA is delivering as a standard product just this time averaged image.
Exactly.
Of course, it is still a bit far away from science-ready data, but still there is really a lot of checks, a lot of this dirty job done. Yes, it's hidden in the script for calibration. Then the PI can simply rerun it by running a script for PI, and script for calibration does it. But these are really many hours of work of checking all these plots and analyzing, and then you flag the data and reanalyze, and then running QA2 report. And again, you find that some antenna is wrong or some subscan, and so iteratively, and a lot of effort is hidden in that. And as you told, finally, the PI or whoever gets the data from the archive absolutely needed to take care of that. Yes, the data are calibrated. You rerun the script, get the calibrated data. You get the time averaged image, which you can immediately set as a model of your time domain imaging. Still, there is a lot of work with self-calibration, with feathering, which we are not providing. By the way, small subset of the solar data, there are like, I think, more than 200 solar data sets now in archive, and around 10%, like 20 of them, are processed using these more advanced methods, and by the effort of University of Oslo. And this higher level data product solar archive is called SALSA. So if you look for already science data ready, as I told, like 10% of the total data so far, but you can find already this higher level data products in that archive. And If not, if you would like to process your data and you are not expert, always you are welcome to visit Czech node for the face-to-face visit. We have the ALMA visitor center here at every node, and accommodation facilities. We are ready to host you here for a couple of days, 1 week, and process your data and make them science ready. This is the key point.
What our contact in Europe. Yeah. Yeah, I wonder if participants have any further questions. We have a big thank you for all this overview on solar data. And if there are no questions, then I think we will close the session, and we invite again participants to contact your nodes if you have questions and you want to work with solar data. And for the rest, yeah, thanks so much, Miro.
One more
I saw you were
request
worried all the time, but it was good.
Okay.
Thank you.
One more request to participants. Yesterday we had a meeting with also American and ARC, and we would like to really to say encourage people to submit proposals. We have too little of them, which I would like that the community has a bigger interest. It is work. We can also help with the proposal preparation,
Definitely.
of course, but we need to keep dynamics and make more proposals.
Yeah. Okay. Well, for next cycle then.
Okay.
We get the pre-announcement, I guess, in December, where all these new capabilities for future cycle, including the ones maybe that you just mentioned. So looking forward to it.
Okay. Yeah.
Okay. Thanks, Miro. Take care, and thanks everyone for joining.